All right, my name's John Barry. I'm going to be talking about social networks and some of the properties therein. Thank you to the organizers for inviting me. So this is joint work with Mike Collins at Christopher Newport University, Aaron Kearns and Jared Saya at University of New Mexico, and Cynthia Phillips and Randy Smith at Sandia. So one of the themes of the previous talk, Jazz's talk, was that with great power comes small, what was the term? I forgot it. Small effects. Okay, so a theme of my talk is going to be, with modern massive data sets come modern massive amounts of garbage. And I'm going to talk about how we came to that realization and what we're doing about it. Okay, so here's some background. We are interested in the problem of a graph, a social network in particular, being stored at multiple sites, and you cannot share the whole graph for whatever reason. For bandwidth, for privacy, whatever, you can't share the whole graph. You can share just a little bit of it, and what can you do? Or you can't share any of it, or you could share a lot of information, but it has to be hidden. Okay, so what we're going to do is set up a model where Alice and Bob have created social graphs GA and GB, or maybe GC, maybe there's a Charlie. There's a overlapping shared namespace and overlapping nodes. So we have GA, GB, GC here. Together, they represent some graph that we want to ask questions about. And the thing is, we have to ask the questions of the individual centers, and we're going to have some bound on the amount of communication that they can do, or some other bound. So you see here, there is a path from S to T, from 37 to 9, but none of them see it unless they work together. Okay. So another model might be that you can share whatever you want, but it has to be, we're going to use this honest but curious model where there's a protocol everyone has to follow. No one's going to cheat on the protocol, but if you give out more information, people will be glad to take that, and you don't want to give out information. So there's a whole field of computer science called secure multi-party computation. That is generally, there are lots of parties and there's a very small amount of data. They're trying to agree on an auction price or something like this, and there are many, many people bidding. This is different because now we have lots of data. We've got a massive data set, and there is a small number of parties. And so this is just a new area. Okay, the motivation, why do we care about this? If companies are going to merge and they want to see what kind of benefit they get out of merging their data sets, without actually giving their data sets to each other, this might apply. In national security, connect the dots type applications, and we're going to say that our nodes are people, and the question is, if we exploit the structure of social networks, can we do better? Can we come up with better algorithms? Okay, so I'm going to talk about three things. First, very simple, ST conductivity. You have two nodes, is there a path? Not even what the path is, but just yes, no, is there a path? Planted clique, and then something that happened when we were looking for planted cliques, and then engineering better test sets. That's the real theme of this talk. Okay, just a few words on ST conductivity. So if you have Alice here in the red and Bob in the blue, and they both store sections of a graph whose union is a big social network, can you find the path? All right. There is a bound, a lower bound on the amount of communication to do this in general, which is n log n. Can we do better if we exploit the properties of social networks? Okay, so here's an easy property to exploit. Social networks typically have a giant component. Probably everyone here knows that. And the second biggest component is usually logarithmic in size, and so that's a very easy property to exploit, and there's literature to back that up. So if we assume that the portions of the graph that have been allocated to Alice and Bob are big enough so that that giant component formed, and that's a reasonable assumption, then there's a pretty natural algorithm that we can apply. So it's just a shell expansion where Alice finds her connected components, and if she has S, if if it's gone into the giant component, we don't send the whole giant component, that's too much. If it's still in a small component, she sends it. As long as it stays small, they can send back and forth. And once they get into the giant component, there's a reasonable expectation that there's a path. Okay, I'm not going to dwell on this. So this is published in IPDPS in 2015. Okay, now things get a little more interesting. So, what if you want to find a dense subgraph? So just audience participation here. How many people here have heard of the planted clique problem? All right, maybe half or quarter, that's good. Here it is. So you have a graph, and an adversary, perhaps randomly, is going to pick a subset of nodes in that graph and make it a clique. And now your job is find that. So there's classical work out there in the computer science theory literature that in an Erdős-Rényi random graph, you can find a planted clique of size root n. And the natural maximum clique size in an Erdős-Rényi graph is size log n. And so that's exponentially worse. So as long as you're willing to find something exponentially bigger than what the real clique is there, the theory says you can do it. And now our question is, well, what if we exploit the properties of social networks? Would we be able to find a smaller clique closer in size to the natural size? That's the challenge there. So I haven't shifted gears into this problem of garbage polluting the graphs yet. This is still what we were doing to try to find this algorithm. So what's going to happen for our experiment is there was a graph, a global graph. Someone planted a clique. And now we're going to give the blue edges to Alice, the red edges to Bob. So now they're going to have sections of that clique, so it's even harder now. And the question is, can they come up with a protocol to find that planted clique? Okay, so now I'm going to talk about a little social network structure and how this leads to an algorithm that should work for this. Okay, with two key assumptions, we do have, in theory, an algorithm to do this. Number one assumption, the maximum degree in the network is O of n to the 1 minus epsilon. It might be square root of n, might be n to the 2/3, n to the 1/3, something like that. So as long as there's, it's sublinear, the maximum degree, and the clustering coefficients for degree d nodes are O of 1 over d squared. So another participation point, how many people have heard of clustering coefficients? Okay, about half. Here's what they are. So you have a vertex in a graph, and you count the number of neighbors of that. If you take that number, choose 2, we call that a wedge. There are d choose 2 wedges. And you look at the proportion of those that close into triangles and divide those things. The triangle is divided by the number of wedges. That's the clustering coefficient. So if you're in a clique and you're disconnected from everyone else, your clustering coefficient would be 1. Okay, with those assumptions, we have an algorithm that will find a planted clique of logarithmic size in the distributed environment. Alice and Bob can go back and forth and they'll find the clique. So that's very nice. Okay, now, the bad news is it doesn't work. So when we look at the social network data out there that you get from the Stanford SNAP library or from the law library in Switzerland, it clearly doesn't work. And so the question is why? And so what we're going to do is back up and talk about some social science that people use to try to understand social networks, and then I'll tell you what I think is new from our work. Okay, so the clustering coefficient assumption of 1 over d squared. So what does this mean? If you look at the average of all the vertices that have degree d and average up all their clustering coefficients and then plot that and keep on plotting it for all d's, it would drop off like 1 over d squared. All right, why do people think that? Well, there's a property called strong triadic closure from Kleinberg and Easley. Two strong edges in a wedge implies at least weak closure. What does that mean? So if I have strong relationships to two people, then there are all kinds of social reasons why they might have at least a weak connection between them. Okay, and there's also a converse of that, that if it's not the case that I have strong relations to you and you, then actually there might be no more than a random chance that you guys would be connected because of me. Okay, so here's another one. How many people have heard of Dunbar's work? Only a few. Robin Dunbar, anthropologist, social scientist, British. So in the 90s, he did some famous experiments and came up with something that people call a Dunbar number. And the Dunbar number is a semi-formal bound on the size of a human community. And does anyone know what the Dunbar number is, kind of, roughly? You look, yeah, so the number that I hear a lot is 150. So what does that mean? It doesn't mean that you cannot have 1,000 relationships. People can have that. What it means is that in order for someone to call a group of 150 people a community, each person in that community has to know something not just about the other individual people, but about the relationships between them. In other words, it's quadratic. So I'd have to know 150 choose two things about a community for Dunbar to call that a community. Okay, he extended that in 2012 to social networks. So now he said, well, you know, what if you have Twitter or LiveJournal or something like that? Does that number fundamentally change or does it fundamentally stay the same? And his conclusion is, it fundamentally stays the same. And why is that? Because we're humans. There are only so many minutes in a day. There's some amount of maintenance that goes into a human relationship, and in order to maintain relationships that would contribute to a meaningful community, you only have so much time in a day to do that. And so who cares if you have Twitter or Facebook? You still have to do something human, and so it doesn't really change. Okay. So this fourth bullet here, this assumption, it's implied. So here's some work by Tammy Kolda and others where they come up with some function psi to talk about the clustering coefficients of a graph based on what they see in data. And it does end up that this is consistent with the 1 over d squared bound I was talking about before. But in practice, it just doesn't hold at all. Not at all. Okay, so if you're going to take anything out of this talk, what I would like you to take out of this talk is this slide. Might even motivate me to see if the laser pointers work. All right. So this is a log-log plot of vertex degree on the x and the per degree clustering coefficient on the y. Remember, this is take all the vertices of degree d, look at their clustering coefficients, triangles divided by the number of wedges, average them all up, plot them. This is what current theory predicts. And this is what we see in practice. So this is Friendster, LiveJournal, Twitter, YouTube, and they're all basically way up here. So those are real data points. So reality is there's something else going on. And in other work, we actually have a new theory of what might be going on with these clustering coefficients. It's actually beyond the scope of this talk. It was talked about by Jared Saya at the WIND conference recently in Livermore. But something's wrong. So I gave you that algorithm that was going to work if the clustering coefficients went like 1 over d squared and the degree was bounded by n to the 1 minus epsilon. It doesn't work. Okay, so here's really why I agreed to give this talk at a massive data set workshop. Here is a couple of pictures from a paper out there, and there are many, many papers out there in the social network analysis literature where this is the clustering coefficients again, but it's not on a log scale. So they go down, and then woo, what's that? And then down all the way. All right. Any conjectures on what this is? It's garbage. Okay, so in an electronic social network, there is some human activity, there are some relationships that are generated by human activity, and there's a lot, as you might expect, there are a lot of relationships that are generated by non-human activity. And just a couple examples here, you can buy 500 followers on Twitter for $5. And that was a few years ago, maybe it's cheaper now. So people want to game their Twitter presence for whatever reason. So there are entities out there that will create these dense networks of bogus Twitter accounts that will now follow you, and wherever you might want to do that. Okay, so we're going to assume that we still want to design algorithms that are going to work on the human portion of the graph so that we can talk about assumptions like I've been talking about the last 5-10 minutes. Those assumptions don't apply at all if there's a bunch of junk from spamming in the network. All right, and in the networks from Snap and Law, the repositories that I mentioned, there's lots of cleaning that needs to be done. Okay, so here's our goal. Clean enough non-human behavior out to test algorithms. It's a simple goal. And for those of you who are wondering where the stats are coming in this talk, they're not, but I'll give you a statistical challenge in a couple minutes. Okay. So we'd like the networks that we test our algorithms on to have some properties. Automated subnetworks, not present. We don't like them. Edges plausibly represent some kind of social interaction. You have millions or billions of nodes, and it's not good enough just to have the ego network of some small set of seeds. We'd like global structure. Okay, the closest that we've seen out there is the Friendster graph. I'll give you some evidence of that in a bit. And I'm not going to say anything about this beater down here. Okay, so this is getting back to Dunbar, the social science, social network theory of Dunbar. So this is a reasonable way of looking at things. So you as a human being have some inner circle of friends. The people who would be willing to come to your house at 1 in the morning and help you if you have some kind of problem. And there's maybe not that many of them. All right, and then you go out one level and basically double that number of people, and maybe these are people who are not going to come to your house at 1 in the morning, but they're good friends and they might help you in some way, etc. 10? Okay. So, there's this 2x expansion out to about 1,500 people, and the typical person might know 1,500 people of some kind. Okay. So here's the definition of edge strength. Actually, a couple of well, Easley and Kleinberg have one. We've got a slightly different one. Consider an edge UV. All right. There are some edges. The endpoints U and V have edges coming out of them. If all of those edges close into triangles, then we would call that strength 1. If none of them do, we call that strength 0. And you have some kind of strength based on the proportion of your edges that close into triangles. Okay, here's, these next few slides are our main contribution from this talk. So I'm showing a notional plot up here where for one vertex, this is for a single vertex, I'm plotting on the x-axis the strength of the ith strongest edge. I really like you, all right? My relationship with you is very strong. All of our neighbors are the same. Okay, you're first. I don't like you so much. So you're after that in the list. And you people out there, I mean, like the people in the back, I really don't like you. I don't have any relationship with you at all. So you're way down there. Okay, so we have this plot for a single vertex. And we're gonna define this to be kind of the ratio, this rank here is the proportion of my neighbors that I've gone through to get to you. And here, this is the strength of our edge. Okay? I'd like to integrate over this and compute some kind of area, but what we're going to do instead is we're going to define something called a strength index, and this is going to be find the biggest square, find the maximum over the minimum of Ri and Si, and then that we're going to call a symmetric strength component, and what we're going to do is define this little S called a strength index, okay? If you were in a disconnected clique, your strength index is going to be 1.0. All of your neighbors are completely strong. All right? So, now, here's an assumption. Assume that the sum of the strengths of the edges coming out of any vertex is bounded by a constant. So this is kind of a generalization of the Dunbar number. He talked about just a community. I'm talking about, or a community, I'm talking about just an edge. And I challenge you, go out to Friendster, Twitter, or something like that, and find me a vertex that has sum of strength, even if it's Justin Bieber and he has 1 million adjacencies. You know, most of those have strength 0. So find me a vertex that has non-constant strength, and you probably will not be able to find such a vertex. All right, so with that assumption, we can do a little arithmetic. Okay, so this capital S is the sum of strengths here. That's going to be bounded by a constant. And actually, if you compute the size of this little rectangle, S squared over degree, we have this nice little model here that says, for any vertex, the S index is bounded by that constant, that capital D divided by the degree square root. Okay, and here's some empirical data saying that, yes, the sum of the strengths and these symmetric strength components, these are real numbers, 20, 30, is basically constant in these social networks. Okay, I'm going to skip that. So here, on these next 4 slides, which I'll flip back and forth from, these are real data from social networks. There's YouTube, there's LiveJournal, there's Twitter, there's Friendster. And what you see here are, on the y-axis is the S index that I just defined, and on the x-axis is degree, and this is a heat map, and these dots are just frequencies. So red is more frequent, blue is less frequent. And what we see here is that, and the green line, this is the square root of some constant big D over degree. The interesting thing is if you look at all these different social networks, they all seem to have this same structure where there is some kind of underlying truth that matches this model. And now here's a very simple idea to clean this garbage out of the network using purely topology, not even worrying about pulling features of the data and doing machine learning and stuff like that. Just if for any degree, for the vertices whose S index is implausible, the Dunbar wouldn't like it, we'll be okay. Remove it. And so what is this stuff up here? So this, let me just give you an example. Here's vertices that have degree 1500 that have S index like 0.65 or 0.7. What does that mean? That means it's almost a full clique of size 1500. All right, and Dunbar wouldn't like that very much at all in terms of calling that human. And our conjecture is that since this is the model of human behavior and this is what the data looks like, probably the stuff here is reasonable to call human, and it's reasonable to get rid of that. Okay, Friendster, there's something about Friendster. So YouTube has garbage, Orchid has garbage, Gowalla, Twitter, LiveJournal, they all seem to have garbage. Friendster doesn't for some reason. Maybe someone can tell me later if you know about these data sets. Okay, so when we do that, if we remove the vertices that violate this S-index bound that I just defined, and we look at what happened, so, and actually you can kind of ignore these sigmas here. These are just numbers of standard deviations above some mean of violation. It's possible in Twitter to remove 0.04% of the vertices. 0.04% of the vertices. And they're incident on 34% of all the edges in the network. So now the moral there is if you're doing any kind of analysis, clustering analysis, statistical analysis on these relational data sets, these networks, probably the analysis that you've done doesn't matter unless you've done something like this first, because it could be that 34% of the whole network is really doing things that you don't care about, if you care about human behavior. Okay, and so when we clean these things and then look at the cleaned networks, they follow a pattern like that. Okay, and the clustering coefficients, remember I showed this horn behavior before? If you start cleaning them out, so the green, the blue, and the pink are clean versions of the network, that goes away and you have reasonable clustering coefficients. Okay. So we've done some validation of this on Twitter just to show out that we're not throwing out humans when we do this, and that is kind of underway now. I'm not going to talk about it. Okay, so I think we have a better understanding of what's going on in these electronic social networks now. We have some new properties to talk about that. We have a suggested way to clean these. And the statistical problem that I promised but actually didn't have in the slides would be, find me a method to fit that green line, which corresponds to this model D, square root of big D over little d, in some statistically defensible way to actually find what that number is, what that generalized Dunbar number is for each network. And we've talked to statisticians about that. We have some ideas, but it's beyond the scope of this talk. All right, thank you. I'm done.